In the previous section, we looked at some of the behaviors of light and its wave properties and particle properties. In this section, we want to look at where light comes from. And before we do that, we need to look at the Bohr model of an atom. The Bohr model of an atom is similar to an onion. So you have the nucleus in the middle, then you have a layer, n equals 1, another layer, n equals 2, and another layer, n equals 3. N equals 4, so on and so forth. And this isn't drawn to scale because in actuality, these energy levels get closer and closer together, as you'll see in a few minutes, as you move further and further away from the nucleus. Now, if this is a hydrogen atom, it would have one electron. And that one electron would be in one of these energy levels. If the energy were in what is called the ground state, the lowest energy level state, it would be in n equals 1. But it could be excited to n equals 2 or n equals 3 if you add some energy. When you have an electron then transition from a higher energy level to a lower energy level, it has to emit energy. And the way that it emits energy is by emitting a photon. And a photon is a particle of light. So this is where light comes from. An electron is thermally, electrically, or excited to a higher energy level by light. And then as it falls to a lower energy level, it emits a photon, and that photon is light. So this is basically what's going on. And this is what we want to talk about in this section. So one thing that's important to realize here that we're going to talk about in a few minutes is that these energy levels are quantized. And what that means is they're discrete. The electron can be in n equals 1 or n equals 2, but it can't be anywhere in between. It could be n equals 2 or n equals 3, but again, it can't be anywhere in between. And what we're going to look at a little bit later is the quantum mechanical model. What we're also going to find is that these energy levels are the places where there's the highest probability of finding an electron. And it doesn't work like everyday physical things where we can know exactly where it is. It works more like a quantum mechanical model where we know where there's a high probability of finding it. So let's look at how we might excite electrons. So in hydrogen, the electron naturally wants to be in n equals 1, as close to the nucleus as possible. And then later on in this chapter, we're going to talk about this quite a lot. But we could get that electron to go to a higher energy level by adding energy. The three most common ways that we can add energy are by adding heat. So on the sun, there are hydrogen atoms that are very hot. Electrons get excited to higher energy levels, and as they fall back down, light is emitted. And you can actually see that light if you look out the window and it happens to be a sunny day, or even not nighttime. Another way is electricity. We can move electrons from lower energy levels to higher energy levels using electricity. I happen to be sitting in a room that has fluorescent bulbs. In those cases, and this is a fluorescent bulb, you have mercury vapor. And adding electricity excites electrons in mercury vapor from a high energy level to a low energy level. As they fall down, they give off light. Mercury tends to give off this bluish colored light. However, companies like GE have developed some sophisticated compounds that absorb blue light and then emit other colors of light. Those other colors of light can be combined to give us white light. Another way we can excite electrons is actually by using light. And believe it or not, you've already learned this. This is how the photoelectric effect works. So if you give an electron enough energy that it can actually fly to past n equals infinity, the highest energy level possible, it will actually fly off the atom. And that's what's happening in the photoelectric effect. The electron flies off the atom and it's attracted to the positively charged plate and a current is generated. So these are three of the most typical ways that we can excite electrons. The next thing we want to look at is this idea of quantized. Quantized in chemistry, or this is really physics, seems like a kind of an out there term and very unique to these things. But it's not. There are things that are quantized in everyday life. In stairs, elevation is quantized. You could be at this elevation on this bottom stair, or I guess this one's the bottom stair. You could move up to this stair and be at this elevation, and you could move up to this stair and be at this elevation. You can't stop at intermediate elevations. So if these stairs are 8 inches tall, I'm not sure how tall the stairs are, maybe 6 or 8 inches, then you could be at this interval or this interval or this interval, but there's 6 or 8 inches in between where you cannot stand. So stairs are quantized. One elevation is allowed, another elevation is allowed, and intermediate elevations, although you transition between them, you can't stop at those intermediate elevations. Now, if you could imagine an escalator where you had a remote control where you could stop it anywhere you wanted. An escalator is not quantized. So we could allow it to go up 1/4 of an inch and stop it, another 1.5 inches and stop it. And we could stop it at any elevation in between the bottom of the escalator and the top of the escalator. Of course, such remotes don't exist, but if they did, you could theoretically do it. So we could think of it in this way as stairs being quantized and escalators being not quantized. Another way I've heard this put is in terms of musical instruments. If you think about a piano is quantized. You can play one note or another, press one key or another. Whereas a guitar is not quantized. Someone who's trained to play a guitar can play any note in between all of the notes. So in this way, a piano is quantized and a guitar is not. So quantized, which exists in chemistry, also exists in everyday things. Remember that in chemistry or physics, quantized is the electron can be in n equals 1, it can be in n equals 2, or it can be in n equals 3, or 4 or 5, but it can't be in between n equals 2 and n equals 3. So here's an example of basically that round atom. So this would be the round atom like this, except for it's written as lines. So instead of the whole round circles around the atom here, we just have a subset of it and it looks like lines. It's much easier to draw, so that's why we use it. So if you look here, n equals 1, 2, 3, 4, 5. Here is n equals infinity. What's important to note is that the nucleus is down here, and as we get further and further away from the nucleus, the energy levels get closer and closer together. So the distance between n equals 1 and n equals 2 is much greater than the distance between n equals 2 and 3, 3 and 4, 4 and 5, and even 5 and infinity. If we have in a hydrogen atom, the ground state is an electron in n equals 1. We can cause the hydrogen atom, the electron in the hydrogen atom, to move up by adding energy, by light, by heat, or by electricity. When that electron falls back down, it'll emit a photon. If it falls from 2 to 1, it'll emit a relatively high energy photon. If it falls from 5 to 4, it'll emit a relatively low energy photon. So an emission occurs when an electron falls from a higher energy level to a lower energy level. Now, if we excite the electron from n equals 1 using light, we can actually use photons, because light contains photons, to cause the electron to jump up. That is called an absorption. So an absorption is going from a lower energy level to a higher energy level using light. Remember the photoelectric effect. If we add a photon of energy with sufficient energy, said another way, with a low enough wavelength, the electron will be ejected past n equals infinity. And then it can go on to be attracted to the positive plate. So these things can absorb energy. And just like the emissions, an absorption from 1 to 2 is much greater in energy than an absorption from 3 to 4. Now, what you learned earlier was that energy and wavelength and frequency are related to each other. So we're going to look at some of those examples in a few minutes. But before we do that, I just want to show you absorption and emission in terms of a diagram. So if light is used to move an electron from a lower energy level to a higher energy level, that's called an absorption. If an electron falls from a higher energy level to a lower energy level, that is called an emission. So this is absorbed and this is emitted. This is exactly what we talked about a minute ago, but we did not have these labels on there. Note that it's also possible to have absorptions from non-ground state energy levels. So for hydrogen, the ground state is n equals 1, because that's as close to the nucleus as possible. And we'll talk more about the electron configuration of atoms later in this chapter. But it starts at n equals 1. It's also possible to have it somehow excited to n equals 2, light, electricity, or heat, and then be further excited from n equals 2. So this is basically how it works. And in fact, for hydrogen, which is very abundant on the sun, any transition from a higher energy level to n equals 1 does not emit visible light. But, of course, the sun emits visible light. We can see it. Well, where does that visible light come from? That usually comes from transitions to n equals 2. These are lower energy transitions, so they can create visible light. These tend to be ultraviolet light. Let's look at how this works. Have you ever wondered how we know what elements are on stars, or what stars are made of? How do we know that there's hydrogen on the sun? Hydrogen on the sun. Nobody went there and collected hydrogen. It's because we have these emission spectrum. If we look at what light is emitted by hydrogen, it's discrete bands. This purple color, this bluish color, and this reddish color. These are discrete bands of light that are emitted by hydrogen. The reason that hydrogen emits discrete bands is because they are related to these quantized energy transitions. So we can actually recognize the elements in different places by taking the light that comes off of them, breaking it into its component colors, and analyzing those component colors. And you'll notice that sodium has some discrete emissions, calcium has discrete emissions, mercury has discrete emissions. Not all the elements are shown here, but they all have these emission spectrum, where they're not emitting all the colors of light, they're emitting specific colors of light. It's worth noting that if you mix specific colors of light together, they do appear white as if they're continuous, even if they're not necessarily continuous, because they're missing some colors in between. So we have here the continuous spectrum. Here is the emission spectrum of hydrogen. If you were to shoot light at hydrogen, you'll have this absorption spectrum. And notice the difference. The emission is the specific colors of light, wavelengths of light, with the specific transitions that occur in hydrogen. The absorption is we shoot light at hydrogen, and now the electrons are going up in energy, and therefore the white light, which is all the colors, is absorbing specific wavelengths that are caused by absorptions. So emissions, light is emitted, we're missing most of the colors, and we have a few specific colors. For absorption, we have most of the colors, and we're missing a few specific ones where the photon interacts with the electron, and it goes to a higher energy level. Now, what this ultimately allows us to do in terms of questions you could be asked is to look at different things like these types of questions, which is which of the following transitions emits the lowest energy photon is the first one. And I want to switch over here to take a look at this. So first, we need to know that if we have n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. These are continuously getting closer and closer together. And on this axis, if you will, we have energy. So this is the energy axis. So let's look at what these different transitions are. And then we could take a look at something about their energy, their frequency, and their wavelength. So let's say, which of the following transitions emits the lowest energy photon? So we want a low energy photon or a low energy transmission, but it has to be an emission. An emission means it starts at a high energy level and it moves down to a lower energy level. So let's look at 1 to 2. If it starts at 1 and goes up to 2, that's not an emission, that's an absorption. We had to add energy. An emission means energy is released. So here we have to add energy, so this can't possibly be the correct answer. N equals 3 to n equals 2. Well, that's an emission. We had an electron at n equals 3, and it falls down to n equals 2. That's an emission. n equals 5 to n equals 4. We have an electron at n equals 5, and it falls down to n equals 4. This is also an emission. Well, which is a lower energy? Well, since the gap between 3 and 4 is larger than the gap between between 3 and 2 is larger than the gap between 5 and 4, this one is lower in energy. So this is a lower energy emission. This is an absorption because you had an electron at a lower energy level moving up. Next, it says which of the following transition absorbs the highest frequency photon? Before we do this, I want to translate highest frequency. High frequency means high energy. So we want to translate to energy before we take a look at this. And I want to redraw this. So this is for question 1, if you will, for question 2. So we have 1, 2, 3, 4, 5. So I'm not going to write 1 every time. Like this. So this is now for question 2. So we want an absorption of a high energy photon, and we translated high frequency to high energy just so it's consistent and we don't essentially have to learn this a bunch of times. So let's see, absorption from 2 to 3, is that an absorption? Yes, that's an absorption because the photon, or the electron is moving up. So that is an absorption between 2 and 3. 1 to 2. 1 to 2 is also an absorption. We have 1, and it moves up to 2. That's an absorption. 3 to 4. We have it at 3, and it moves up to 4. This is also an absorption. So all of these are absorptions. So we can't cancel any of them out. Now, which is the highest energy? Well, the one that is going to be the highest energy is the one that's the biggest gap. So 1 to 2 is a large gap. 2 to 3 is smaller, and 3 to 4 is smaller still. Since this is the largest transition, it's the highest energy transition, and is the answer. Last one. So I'm going to draw this for number 3, and I'm going to draw the same thing. 1, 2, 3, 4, 5. Here we have, it says, which of the following transition emits the longest wavelength photon? So again, we want to translate. Long wavelength means low energy. So we want to know which of the following transitions emits the lowest energy photon. Again, if I translate the frequency and the wavelength into energy, then I only have to learn one system, as opposed to learning this if it's labeled for frequency and if it's labeled for wavelength. So I translate to energy, low energy. So now we have emissions of low energy, 4 to 3. 4 falling down to 3 is an emission. 2 to 1. 2 falling down to 1 is an emission. 3 to 4. 3 going up to 4 is not an emission. That's an absorption. So that can't possibly be the answer, and we can cancel that one out. So now here we want to look for the lowest energy one. Well, an emission from 2 to 1 is this much energy. From 3 to 4 is this smaller amount of energy. This is a lower energy transition. I think I said 3 to 4, but I meant 4 to 3. So 4 to 3 is the lowest energy emission of these choices. So this is basically how we can use this. Remember that these individual transitions that occur lead to these line spectrum. So these are the actual wavelengths of light that may be emitted based on these energy transitions. The last thing we want to look at is, well, how can we actually calculate the energy of this transition? And to do that, we want to use something called the Ridberg equation. And the Ridberg equation only works for hydrogen. And it says delta E equals negative 2.18 times 10 to the minus 18 joules times 1 over NF squared minus 1 over NI squared, where E is energy in joules, NF is the final energy level of the electron, and Ni is the initial energy level of the electron. And this is called the Ridberg equation. I will note that you can get constants for the Ridberg equation in other units. You can find constants for the Ridberg equation in frequency units. This becomes 1 over lambda, and then this is in, in wavelength units. This becomes 1 over lambda, and then this will be in wavelength units or meters. That's why you can find different examples of the Ridberg constant. The Ridberg constant I'm showing you here is in joules, which is a perfectly valid one to use. There's good reasons to use the other one too if you're looking for wavelength, but in this case you can find it here. Remember that if you calculate energy, you can convert it to wavelength using E equals hc over lambda. So let's look at the example here. It says calculate the energy of the transition from n equals 4 to n equals 1 in a hydrogen atom. So delta E equals negative 2.18 times 10 to the minus 18 joules times 1 over n final, the final energy state is 1, squared, minus 1 over n initial, which is going to be 4 squared. So that's basically how we're going to do this. So delta E equals negative 2.18 times 10 to the minus 18 joules times 1 over 1 squared is just 1, minus 1 over 4 squared, which is 1 over 16. Delta E equals negative 2.18 times 10 to the minus 18 joules. 1 minus 1/16 is 15/16. And when you do the math, you find that delta E is equal to negative 2.04 times 10 to the minus 18 joules. Now, much like other thermodynamic things that you learned in this quantum mechanical application, we want to consider whether it's negative or positive. So if we have 1, 2, 3, 4, we had an electron fall from 4 to 1. This is an emission. The atom is the system. The atom lost energy. It had an electron at a high energy level, and now it has an electron at a much lower energy level. So the system, the atom, hydrogen, lost energy. So delta E is negative. As a general rule, delta E is negative for emissions, delta E is positive for absorptions. If you were to subtract backwards, if you took Ni squared minus Nf squared, you would get the exact same number, but it would be positive. So it's always a good idea to double check, if I get a negative delta E, did I have an emission? Or if I get a positive delta E, did I get an absorption? So these are different ways in which we can actually calculate the energy. We can determine whether an emission or an absorption has occurred, and this explains where light comes from. So on the sun, it's very hot. Electrons are excited to higher energy levels. When they fall to lower energy levels, massive amounts of energy are emitted in the form of photons.